Okay, so welcome to day one. So today there will be three lectures and 2 hours of tutorial. So tutorial what we have planned, we are going to give you questions and you have to try, and maybe we are going to give you hints regarding that, and one or two questions maybe we are going to solve them. Okay. Uh, so uh, So we will start today with this definition, coloring. What is a coloring in graph, right? So this notation we are going to always follow. G is a graph with vertex at V and S at E. Sometimes we are going to write S set of G and vertex set of G, right? And these graphs, mostly we are going to consider simple graphs, undirected graphs if it is not specified, right? So when I am saying a graph, then you try to assume that the graph is simple and it is undirected. Okay, suppose G is a graph, let G is a graph. Let G is a graph, let G be a graph, then a function, let us say define phi to the vertex set to a set such that phi of u is not equal to phi of v if u and v is an edge of the graph. We call this function, f a coloring on G, fine. Okay, so let us see an example. Let me take a very simple example. This is this thing. So how we can color this thing? We can color basically this one by red, let us say this one by pink, right? And let us say this one by green. So if we color like this, then is it satisfying our condition? Let us say this name is A, this is B, and this is C, right? Is this condition is satisfied, right? So in fact, this coloring also we say that proper coloring, right? Coloring, or simply we say that it is proper coloring. Proper is basically if two vertices are adjacent, they are going to receive different colors. And the same graph, let us say 1, 2, 3, 4, 5. Let us take another graph. So here I can color basically this one by red, this one by pink, this one by some other color, this one by green, then this one by another green, this one by, let us say, brown, right? So this is also a coloring and it is also satisfying. So what is the difference between this example and this example? Number of colors. You can see that in G2 we can we are using basically 1, 2, 3, 4, 5, 6 number of colors, but we can do that thing with basically, if I am giving this one red, then let me take this is blue, this is red, then this is blue, and this one red, and this one. Okay, so this one with the blue. Okay, so basically here two colors we are able to do that, right? So there comes basically the minimum number of colors, the minimum number of colors used to do proper coloring on a graph. Proper coloring on a graph is called the chromatic number of the graph, right? And it is basically denoted by a notation, let us say chi of g, right? So if we want to mathematically define this one, then basically we can write chi g is basically mean over k such that g can be proper colored using k colors, right? Okay. So we are going to tell this thing also a proper k coloring. Proper k coloring means k number of colors are used to do the proper coloring on the graph. So, what can be the largest number of colors for this? It will be basically number of vertices, right? So if we take basically chi g, then it will be at most this one, right? So can we improve this one, right? So can we use less number of colors for this instead of n? Can we make the graph proper k colored where k is strictly less than, right? So let us see some example and then. So I have already shown chi of kn is n, right? So what about chi of Cn? Cn is the cycle on n vertices. So what is chi of Cn? This is you can check. Let us say this graph. How many colors? We can color one. You can color with color number 2. We can color this one is color number 1, color number 2, then need 3, right? So whether it is 3, chi of Cn is 3. Okay, good. So whatever, so it is basically 3 if n is odd, it is 2 if n is even, right? And what about chi of kn? Kn is a complete graph on n vertices. What is chi of n kn? This is n, right? So what can we say about these two graphs? One graph is having large chromatic number, another graph is having small chromatic number, right? So can we get bounds on this thing? So that is basically we are going to talk about basic bounds. Okay. So already we have seen chi of g will be at most n, right? So chi of g is at most n. So in this case, we have this example chi of n, kn is basically n. Are we having any other example where chi of g is exactly n? may not are having the thing, right? So let us try to, so whether we can improve for what graph, this will be this thing, right? So let us say what can we say, that suppose H is a subgraph of G, then can we say this result chi of H is at most chi of G? Why? Basically, let us say this is our graph G, and here we are using k number of colors and H somewhere over here. So if you restrict the color of G on the subgraph H, then we are going to see that it will the number of colors of H will be at most the number of colors used to color the graph G, right? Let us say omega G, omega is basically the click number. So what is click number? It is the largest subset of vertices which induces a complete subgraph of the graph, right? So what can we say about chi G in terms of omega? What can we say about chi G in terms of omega of G? So you try to use over here, right? Let us say this is the subset of vertices which is uh, inducing a complete subgraph. So let us take that is our H. Then by this, what will happen? Omega of G is less than equal to chi G, right? Whether chi G is greater than equal to omega, sorry, chi G is less than equal to omega, is omega G can be larger than this, right? Whether this will be? No, because you take C5, very simple example, C5, you take C5, then what is omega here? 2, and what is chi over here? 3, right? So this may not be true. Okay, what about whether chi G is always equal to omega G? No, right? Whether this is always chi G is equal to omega of G? It may not be, right? Because you can see this example also, right? And now let us think in other sense. So let us say that phi on this vertices is basically set we are taking, let us say, without a less loss of generality, k number of colors, then let me take Vi is the set of vertices such that phi of V is assigned, the V is assigned color I, okay, fine. So what about Vi? What can we say about Vi? Vi is an independent set, right? Vi is an independent set, right? Let me take this is for all I belongs to 1, 2 up to k, okay. So Vi is an independent set. Let us say this is my V1, this is V2, like that this is Vk, right? So what about Vi? the cardinality of Vi will be, Vi is independent, right? So the cardinality of Vi will be less than equal to alpha G, where alpha is the maximum size of an independent set, right, or independence number. So what can we say about if we, and you can see that what about Vi intersection Vj? So this is basically they are not going to share any common vertex, right? So what can we say about if we sum I equal to 1 to k, then what will happen? This will be k times this one, right? Okay. So k if k is the chromatic number, if k is chi g, then what will happen? We can say that chi g is greater than equal to n by alpha of g, n by alpha of g, right? For any graph, can we get a better bound than n actually? N is less than equal to n, n is very large bound. So can we get a better bound, right? So that is basically the next proposition. For any graph G, we have chi G is at most delta of G plus 1. Why? You can see that, let me take, this is a vertex of degree delta, right? D of V is delta, right? Then how to color, how many colors this V and neighborhood of the V and the open neighborhood of V will require? So these many colors, they are in the worst case they are going to have delta number of colors, and we need to give this one with delta plus 1 color, right? So because of that, this is basically the chi g is at most delta G plus 1, okay. Okay, so can we actually get a procedure to color a given graph, right? Using this thing, can we get a procedure to color the given graph, right? So let me write the graph. Let us say this is a graph with n vertices, right? The vertices, let us say v1, v2, like that, vn, v1, v2 up to vn. Then suppose we are able to order this one, right? Then and we are trying to color them, right? And how we are going to color? Let us say that we are going to color them with this order. We need to color v1 first, then we are going to color v2, then like that we are going to color vn, right? So if we are doing like that, then what procedure, what rule we are going to follow? So suppose v1 we have given the color 1, right? So v2, which color we are going to give? 1 or 2, right? So it is basically 1 or 2, right? And similarly, what about v3? 1 or 2 or 3, right? So why this thing we are giving like this? We are checking basically whether the current vertex Vi, how many neighbors have appeared before Vi with this order, right? So this thing is called a greedy coloring algorithm, right? So let me formally write this one, greedy coloring algorithm. So an ordering of V is given, an ordering of vertices is given. Let this ordering be V1 to Vn, right? So step 1 is color V1 by 1. Step 2 is once V1, V2 up to Vi minus 1 are colored, color Vi with the least available color, right? So least available color means we are going to check whether 1 is available, whether 2 is available, right? And how you are going to check? We are going to check with the neighbors of Vi whether they have received this color. If they have not received any color, then you just give it to Vi. If all the I minus, if all the neighbors of Vi have received the color, then you just give a new color to Vi, right? So let us try to see one example. You consider a C6. Let me take U, V, W, X, Y, Z, and let us take an this is U, V, W, X, Y, Z, right? So let me take this order U, W, V, Y, Z, X. Now let us try to color them. So if we we are going to give color 1. What about W? W is not adjacent to U, right? So we can give W also color 1. Then V, we need to give color 2, right? Y, Y is not adjacent to any of them, so we can give 1. Z, Z is adjacent to U and Y, so we are going to give it color 2. What about X? X is adjacent to Y and W, right? So we can give it color 2, right? U, now let me take another order U, X, V, W, Z, Y, right? So we can give color 1, X, X also we can give color 1, V, V is adjacent to U, so we need to give it color 2, W, W is V and this, W will be 3. What about Z? Z is U and Y, so Z will be, we can give color number 2 to Z. What about Y? Y is 3, right? And what is C6? C6, it is an even cycle, so it can be 2 colored, right? But here what we are getting, with respect to sum ordering, we are getting more number of colors to color the graph C6. So what observation we can think of here? that this greedy procedure may not give us the optimal number of colors, right? So, observation, we can put it as an observation, greedy coloring algorithm may not give the optimal number of colors, right? Spanning trees, you know what is spanning trees, right? It is basically a subgraph of the graph having the vertex set at the vertex set of the original graph, and it is a tree. Okay, so spanning tree, right? And how to get a spanning tree of a graph? Suppose I am giving you a graph G. How to get a spanning tree of the graph? By deleting the edges of the cycle, we are going to get a spanning tree, right? And also there are procedure how to get a spanning tree, right? So here the let us try to see one thing. Suppose a graph G contains a vertex of degree dv less than delta G, then what can we say about the chromatic number of the graph? Graph is having a vertex whose degree is less than delta. Chromatic number will be, can you say that less than equal to delta of G? How? Yeah. So you take an ordering of the vertices. So let me take basically V1, then V2, right, like that, up to V. So you want to tell this one, this is V, then whether it will satisfy, whether with respect to this we are going to get uh, the number of colors will be delta. Let us assume that this graph is connected, the graph G is connected, otherwise we can do with component of the graph. Then whether it will be delta, what about this vertex? Let me take, this is Vi, right? This is another vertex which is having delta degree, and all its neighbor have appeared earlier. Then what will happen? It will give us basically delta plus 1, right? So which ordering we have to take? That is the question, right? So carefully we need to find this ordering. So let me take, this is the vertex V, right? So I can take a spanning tree of the graph. Let me take, let T be a spanning tree of G, right? And it is an undirected tree, spanning tree. So we can make in every node, right, any vertex to be the root of this spanning tree, right? So let us take this V spanning tree of G having root at the vertex V, right? So how it will look like? Let us say this is V, right? Then it is going to have some neighbors, right? Not all, okay, it is going to have some neighbors. Then okay, since it is root, so all the neighbors will be there, okay. Then it is having some neighbor, this is having some neighbor, this is having some neighbor, like that, okay. So what we are going to do, we are going to write the vertices with respect to the level, right? So whichever is at the bottom, you write them first, right? So it is like uh, here if we name, these vertices will come first, then these vertices will come, then these vertices will come, then this vertex will come, right? So if we write the ordering in this respect, then what will happen? You can see that for every vertex except V, there is a neighbor which will appear after that vertex, right? So this property won't be there. For Vi, all the neighbors are not appearing before it, right? If we write like this, then for every vertex, we can say that for every vertex, there exists, let us say for every vertex X, there exists a neighbor of X appearing after, right, after X, right, in the order, right? And what this X is not equal to V, X is different than V, right? So now apply greedy algorithm, greedy coloring algorithm. Then what will happen? For every vertex we are having at most delta minus 1 neighbors appearing before that vertex in the order, and there will be another vertex which will appear after it, right? So what will be the color for this vertex X? We can give with the delta the color number delta to this vertex, right? And except V, for V how many neighbors are there? Less than delta neighbors are there, right? So because of that, we can say that in this case chi G will be at most delta, right? So one more proposition I want to do. if G has a cut vertex V, right, then what can we say about chi of G? Is it true? Chi of G delta G? Is it true chi of G is at most delta G? So we can make here delta, let us say delta G is a graph with G is a graph, connected graph with delta is greater than 3. Delta of G is greater than equal to 3. Less than equal to 2, whether it is true, it is having a cut vertex. Right. So let us say delta is greater than equal to 3. Okay. So we will see what will happen for delta less than equal to 2. Okay. So how to do this one? So V is a cut vertex you know, right? Cut vertex, it is a vertex. If you remove the vertex, the graphs become disconnected, right? So let this V be the cut vertex, right? And this is basically the graph, and here this part, let us say this is G1, this part let us say this is G2, right? Right? Okay. So what about degree of V in G1? This is less than delta, right? What is degree of this is less than delta, right? So this is less than delta, this is also less than delta, right? Right. So G1 is what is chromatic number of G1 uh, is at most delta, and chromatic number of G2 will be at most delta, right? So can we out of this, let us say you take a coloring, delta coloring of G1 and delta coloring of G2, right? So out of these two coloring, can we make a coloring, delta coloring of G, right? So we can make a, how we are going to make? So let us say uh, this is 1, right? This is color number, whatever the color number, and you try to, since this is delta color, so if it is receiving color 1, right, color 1 in this graph G1 and color 2 in this graph G2, then you exchange the color of this vertex, and accordingly if needed you change the colors of G2 to get a delta coloring of G2, right? and because of that we can say that, okay, we can say that let us take let phi be a proper delta coloring of G1. Let me take phi 1, phi 2 be a proper delta coloring of G2, right? Then what will happen? Then um, if phi 1 of V is not equal to phi 2 of V, then changing or permuting the colors, the colors the coloring uh, of the vertices of G2, we can get a delta coloring of G, right? Okay. So therefore we can say that chi of G is at most delta of G, delta of G, right?